Hi everyone! I wanted to make a video for lesson 1.4 because it did not get recorded with our class for Zoom. Now remember, you can find these guided notes in a folder in our course materials. So you are welcome to print these off just to expedite the note-taking process, or you can write this down if you like. If you're writing it down, then I ask that you probably want to pause the video now and then to write down some things, because I'm going to go through this pretending like you already have this printed in front of you. And so lesson 1.4 is about types of functions and rates of change and constant and linear functions, and hopefully you'll remember some of this stuff from your high school math courses. So we begin with a discussion of rates of change and a practical example about cell phone plans. So we have two plans here. We have an unlimited minutes plan, and we have a pay by the minute plan. And what we're supposed to do is we are going to find and interpret the rates of change for both plans. So let me begin with, I'm going to call this Plan A. And notice that there is no change from 100 minutes to 200 to 300. It stays $199 whether you use 100 minutes or 1,200 minutes. So for the rate of change for A, I would say it's 0. There's no change. And to interpret that, I would simply say that using additional minutes does not result in a 0 cost increase. So I'm just going to say, let's see, how do I want to say that? I'm going to say there's no cost for additional usage. No cost for additional usage. Now, the next plan, pay by the minute plan, I'm going to call that Plan B. And Plan B, there is some things going on here. So for Plan B, each time you use 100 more minutes, the additional cost is $20. Okay, so again, if I use another 100 minutes, it's going to be another $20. And so there is a mathematical rate of change. And so I should introduce rate of change. Rate of change, which I'll just put ROC for rate of change. And it is defined by the change in your y values over the change in your x values. And that triangle is actually a Greek letter delta, and it's used in math and science universally to represent change. So we have the change in our y values divided by the change in our x values. Now our y values are going to be in the second row, and those are changing by $20 in this case. And our x values, let me erase this little mark here. Our x values are changing by $100. So for B, the change is $20 for every 100 minutes. We could reduce that. If we divide 20 by 100, we're going to get 0.2. And so if we interpret that, let's think about that. So it was $20 for every 100 minutes. So now it's going to be 0.2 or 20 cents for every minute. And so that's really the cost. Okay, so there's a 20 cent per minute fee. We could say I mean, basically that's what's happening. It looks like they may charge you in chunks. But if you're spending $20 for 100 minutes of cell phone usage, then that equates to 20 cents for each minute. And so that's what's meant by rate of change. So you'll see this change in Y over change in X. And another thing you might recall from your high school math courses is there's a formula. How do you find how something changes? Well, you take a Y value and you subtract the previous one, and that tells you how much it changed. So if you look at this table, if you take 59 and subtract 39, you can see that you get 20. Or you could take 79 and subtract 59 and get 20. So a Y value, we'll call it the second Y value minus the first Y value, tells you how much Y changes. And then for X, we see that the X's are going up. You could take a second X value and subtract the first X value. So you could take 200 and subtract 100 and see that the change is 100. Or you could take 300 minus 200 and see that the change is 100, and so on. So that formula might look familiar to you. Often we represent it with the letter M, and it also means slope. And so we can find the rate of change from a table by looking at how much the Y values change and how much the X values change. And being able to interpret what in the world that means is also very useful. Now here we have a graph of the situation, and sometimes that's very helpful as well. So we can see for plan A, this unlimited plan is represented here. Okay, this is plan A, that's unlimited. It looks like it's $200, but we recall that it's $199. And so we call this a constant graph because it is a horizontal line. It never changes. There is zero slope to it. The rate of change is 0. And if I wanted to write an equation of that line, I would simply say it's Y equals $199. I might use C instead of Y for cost, but it's just one simple equation. And all horizontal lines have an equation Y equals some number. Now, the other one is a little bit more interesting. Okay, so B is this other line, and we see that, again, it has a slope, so you could pick a couple points, and you could do rise over run. These points are difficult to read because we know we can look up here and see for 400, what was the cost? 400 for plan B was $99. So this point right here is 400, comma, $99. And this other point that I've highlighted at 900 minutes, let's see, for 900 minutes okay, that's where they're the same, $199 for plan B. And so for 900 minutes, the cost is $199. And so you might remember from your high school math course that you could find the rate of change by rise over run. So remember, this line here goes up to 199. So the change from 99 to 199 is a change of $100 or 100 minutes. And then the change here, $100, isn't it? And then the horizontal change from 400 to 900 is 500. And if you divide that, guess what you get? 0.2. Okay, your 20 cents. Now, for something like this, if we wanted to write an equation, you might remember your y equals mx plus b. From your high school math course. And so you could find the equation of this line. The slope is 0.2, 0.2. The b is your y-intercept, okay? So m is slope, b is your y-intercept, where it crosses the y-axis, right here, whatever this is. And it's kind of hard to tell. It's somewhere between 0 and 50. I'm not exactly sure. And I honestly think it might be easiest to find this if we go back to the table. It's asking, okay, what's the cost for 0 minutes? And the table didn't tell us that, but if we continue the pattern of the table backwards and we add a column over here to the left, and we call it 0 minutes. So let's see, the change here from 0 to 100 is 100. The change here is 20. So if we go backwards $20 from 39, 39 minus $20 is 19. So basically for this plan, if you use 0 minutes, it's going to cost you $19, according to the pattern at least. And so what that tells me at this point right here is 0, 19. That is my y-intercept. That's my b. So plus 19. So we can find this information, the slope, the y-intercept, from a table. We can find this information from a graph. Now, the first one, the constant, that one was the first plan that doesn't change. And then the second plan was a linear function. And so here we have the general forms written for us here, the constant and the linear function, which we just kind of looked at a little bit. Notice that because in a constant function the slope is 0, it really could use the linear function. If you plug 0 in for m, you're going to get f of x equals 0x plus b. And of course, 0x's can just fade away since that's going to be 0. So here, what we want to be able to do in this next activity is just identify whether a function is constant or linear or nonlinear. And so we're going to kind of look back at the general forms. Constants are going to be easy to spot because it's just going to say f of x equals some number. Just a number, no x at all. For a linear function, it's going to be some number times x plus another number. And if it's not one of those, then it's not a constant or linear. So let's just kind of take a look at these examples here. Erase that. All right, so for this first one, it doesn't look like either one of those. It has these absolute values. So it's not linear or constant. So it is nonlinear. All right, this is called an absolute value function. And I don't know if you remember from your high school algebra, but an absolute value function, when you graph it, it looks like a V. So it's sort of like two rays with the same endpoint, to speak geometrically. So it's kind of linear, but it's kind of like two lines. This next one is also nonlinear, and I know this because of the x squared, okay? The x squared. That is not linear. You might recall from your high school algebra course that if you have an equation with x squared, it's going to be a quadratic equation, and when you graph it, it will look like this. We call that shape a parabola. And certainly that's not a line. The next one fits the bill because we have, now we're calling it h of x. You can call a function f of x, h of x, g of x, any of the things. This one, h of x, is equal to 2x minus 6. That fits with our mx plus b, where m is 2 and b is minus 6. So this fits the linear bill. So this is clearly linear. Now it said check 1, and I'm putting x there, but I think that's okay. Finally, we have another nonlinear because we have another absolute value graph. This is going to be shaped once again like this. So the one above, I guess to fill in a shape, it's definitely going to be a line where the slope is 2. So if you were to pick a point and another point and do rise over run, okay, so the change in your y values here, your change in your x values. So if you did your change in y over change in x, it would be 2. It would simplify to 2 at least. And then of course your y-intercept, so that's your m value. Your y-intercept b is negative 6, meaning that that line would cross the y-axis at negative 6. All right, one more. We have z of x is equal to pi. Now pi is a number. Pi is the number, it's an irrational number, meaning the decimal never ends, but it's 3.1416 and so on, and it keeps going. But it's still a number, and so if we have a function that just is equal to a number, we know that that is a constant, and we know that if you graph it, it's just going to be a horizontal line. It's going to cross the y-axis at, guess where? 3.1416, blah, 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 blah. All right, let's continue with our discussion here. It says, what kind of equation can be graphed using a slope and a y-intercept? Well, that would be a linear function. That's your m, slope is your m, and y-intercept is your b. Now, I often wondered for years, why in the world would we call slope m and y-intercept b? And I got to thinking about it, and the best explanation I've come up with is if you are graphing a line, you would begin with your y-intercept. You would plot that point, and that's where you would begin, along your y-axis, whatever your y-intercept is. And the slope is how you move from one point to the next. You rise and you run, you rise and you run, then you can draw your line. I'm not sure if that's what was intended when M and B first came on the scene, because that was before my time even, believe it or not. But that's a good explanation that I can come up with. Number 4 says, what does the graph of a constant function look like? Well, remember, a constant function, pretend like that's a straight line, looks like that. It is a horizontal line. Number 5 says, describe a way of graphing equations that cannot be graphed using a slope and a y-intercept. So for example, if you wanted to graph one of those other ones we looked at earlier, like a quadratic or maybe an absolute value graph, or maybe think about when you very first started graphing functions, what did you do? You might remember that you could make a table of values. You might remember where you would make one column X and one column Y, and then you would select your own X values and then plug those in and figure out what Y value goes with it. And then you could just do that for several different points until you start getting a picture, an idea of what the graph looks like. Sort of like just connect the dots. So number 6 says, from the table on the previous page, choose one linear and one nonlinear equation and graph them below. Now I remember we were kind of talking about this one, y equals, or I can't remember what it was called. Let me go back and look. The one we were looking at, this one, h of x equals 2x minus 6. Let's graph that one. Now h of x is just the name of the function, and it's a very fancy way of just saying y equals. We get our y values by taking 2 times the input, subtracting 6. So remember, our slope, this is our m value, this is slope, and minus 6 is our y-intercept. So remember, we begin with the minus 6. So if I'm sketching this along the y-axis, I'm going to go down to where I think minus 6 is, right here. So this is the point 0, comma, minus 6. It's my y-intercept. Now my slope is 2, my rate of change is 2, and usually we think rise over run. So you may want to think of slope as 2 over 1. We can write any number as a fraction if we put it over 1. And so you would rise 2 and you would run 1. So your change in y is 2, so you would go up 2 and over 1, and that would lead you here. And you could do that again, up 2 and over 1, and that would lead you here. And then you could go up 2 and over 1, and that would lead you here. And so you could keep doing that and get a nice line. Okay, that's not so great, but it's a sketch, and you can see how you could do this. Now, the nonlinear, it helps when you kind of know the basic shape. Let's go to the quadratic and look at how we would do that. What was the quadratic one? Whoops. The quadratic was this one, g of x equals x squared minus 5. Let's take a look at how we would graph that one. Put a little graph over here. So what we might do is we might just make a table of values. And we might just try some points. Like we might start with 0. If you plug 0 in for x, what do you get? 0 squared minus 5. Well, that's just minus 5. So 0 minus 5. Make a dot. And then I might try, what about 1? If I plug in 1 squared minus 5 is negative 4. Okay, 1 squared is 1. 1 minus 5 is negative 4. So then 1, negative 4 might be here. And what about 2? 2 squared minus 5. 2 squared is 4. 4 minus 5 is negative 1. So 2, negative 1, maybe up here somewhere. And maybe 3. 3 squared minus 5. That's 9 minus 5 is 4. So that's going to be way up here. And then maybe I start going with some negatives. What about negative 1? Negative 1 squared is 1, and 1 minus 5 is negative 4. So negative 1, negative 4, which would be right in here. And maybe I try negative 2. Negative 2 squared is also positive 4. When you square a negative, you get a positive. Minus 5. So 4 minus 5 is negative 1. And so you can kind of see the parabola taking shape here. Obviously, that's a very crude graph. But nonetheless, it looks something similar to that. So a table of values is also a good option. Oh, I didn't realize I had graphs for those. All right, I can make those a little nicer. So negative 6, 1, 2, 3, 4, 5, 6. And then rise 2, run 1. Rise 2, run 1. Rise 2, run 1. So up 2 over 1. You could just keep doing this if you wanted. I like to do that. And then another interesting thing you can do is to fill in the bottom part, you could do the opposite. Go down 2 and left 1. And then you've got a nice guide to draw your line. Over here, the points were 0, 5, 0, negative 5, 1, 2, 3, 4, 5, 1, negative 4, and I think we had negative 1, negative 4. Parabolas are very symmetric. We had, I don't remember what 2 was, 2, negative 1. Sorry, my phone's buzzing over here. Let me get rid of it. And then negative 2, negative 1. We also had 3, 4. 1, 2, 3, 4. Oops, here. And for symmetry, I know that negative 3, 4 would also work. And so we've got this nice points to guide us here. Forgot about those graphs. All right. Here we're going to find the rates of change between adjacent points and determine whether the function is linear or nonlinear. Okay, so from a table, we saw earlier how to find the rate of change. We're going to do the change in the y value divided by the change in the x value. So let's just test these out. So let's look at how much the y values are changing. From 19 to 15, that's a change of negative 4. Remember, you always do a y value minus the previous one. So 15 minus 19 is negative 4. And then from 15 to 12, that's a change of minus 3. 12 minus 15. And then 8 minus 12, that's going to be a change of minus 4. And then from 8 to 4 is a change of minus 4. Now, don't fret that those aren't all the same just yet. Let's check out the top. So from negative 5 to negative 3, you could do negative 3 minus negative 5, and you're going to get positive 2. From a negative 5 to a negative 3 is a change of positive 2, because negative 3, think about a number line. Negative 3 is to the right of negative 5, so it's bigger. And then from negative 3 to negative 1, we go up 2 more. And from negative 1 to 1, we go up 2 more. And from 1 to 3, we go up 2 more. And so if I put the change in y over the change in x, it would be, for this first one, the change in y is negative 4, and the change in x is 2. And negative 4 divided by 2 is negative 2. If I look at the next one, the change in y is negative 3, and the change in x is 2, and that's negative 1.5. Now the others are obviously going to be negative 2, but we've got this one odd duck. We've got one point that doesn't quite fit. And so when it says in the question, find the rates of change between adjacent points, and determine whether the function is linear or nonlinear. Because of that one odd duck, I'm going to say that this one is nonlinear. It's almost linear, but if it's truly linear, then the rates of change will always reduce to the same number. Let's look at this next example. Let's see how we're changing here. Here, if you go from -8 to -2, that's a change of +6. You're going up 6. So you could do -2 minus -8, and you would get +6. And then from -2 to +2 is a change of 4. From 2 to 4 is a change of 2, and from 4 to 10 is a change of 6. Now let's try our x values. From -4 to -1 is a change of +3. From -1 to +1 is a change of 2. From 1 to 2 is a change of 1. And from 2 to 5 is a change of 3. So let's check out these change in y over change in x. Don't forget to put the change in y on top. Sometimes we mess that up. So for the first set of points, the change in y is 6, and the change in x is 3, and 6 divided by 3 is 2. For the next set of numbers, the change in y is 4, and the change in x is 2. But 4 divided by 2 is also 2. So we have some consistency going here. We would say that's a constant rate of change. And then the next one, the change of y is 2, and the change of x is 1, and 2 over 1 is 2. And finally, we have the change in y is 6, and the change of x is 3, and 6 divided by 3 is also 2. Because these have the same rate of change, then this one is linear. It's a perfect line. The next thing I want to talk about here is intervals of increase and decrease. So in a graph, you should be able to, no matter what kind of graph it is, and clearly these are not linear, you're going to want to be able to tell where is the graph going up and where is the graph going down. And when you determine this, you're going to read this like you would read a book. You're going to read it from left to right. And you're going to read the x values. So you're going to read the numbers along the x-axis here. Okay? So when we begin, we're going to begin at this point, and we're going to be going up. We're going to be increasing until we get here. And that interval of increase starts at an x value of -2, and it goes to an x value of 0. So again, I'm reading the numbers, the x values of the number. This point has an x value of -2. This point at the top of the curve has an x value of 0. Next, we're going to go down. So from this high point, if I keep traveling from left to right, I'm decreasing until I get here. So I decreased from an x value of 0 to an x value of 5. Okay? And I know that the way that I'm writing this looks like points, but these are just intervals. These are x value intervals. Now once I get to that low point, I'm going to start increasing again. And I'm going to keep increasing until I get to this point. So I increased from an x value of 5 at the bottom of the curve, and then I increased until I got to an x value of 8. And when you have more than one interval, you're going to combine these with a union symbol, a U. I only have one decreasing interval, and I have two increasing intervals. Now for these, you're always going to use parentheses on your intervals of increase and decrease because at the end points, the function is neither increasing nor decreasing. So again, think about starting this journey along this graph at the beginning. And when you begin, are you increasing or decreasing? Well, you might argue that you're about to increase, but if you're just standing on this dot, you're not doing anything. And then you increase until you get to this high point. But when you're on this high point, you're neither increasing nor decreasing. And then you decrease until you get to the bottom. And once again, here at x equals 5, we call that a turning point on the graph. We're not increasing, we're not decreasing, we're just turning. And then we increase until we stop. And so intervals of increase and decrease are always going to have parentheses rather than brackets. Let's look at this next example. I think this is the last example. If I'm trying to go from left to right here, it's a little bit problematic because I am starting at negative infinity. There's really no place to start. And when I do start, wherever I hop on, I'm going to decrease until I get here. Okay, so where did I start decreasing? Well, I started decreasing way over at negative infinity. And I decreased until I got to an x value of negative 2. Don't forget to read your x values. Then, again, always from left to right. And then I start increasing until I get here. And so I increased from an x value of negative 2 to a y value of positive 2. And now I'm going to start decreasing again until I get to the end. And I decreased from an x value of 2 to an x value of 4. And since there are two intervals of decrease, I'm going to combine them with a u. So we have looked at constant and linear functions. Constants are your horizontal lines. Linear functions have some sort of slope, some other y-intercept. And we should be able to look at those graphically from a graph. We should be able to find them analytically from the equation and also from a table. And then we added this additional idea of increasing and decreasing intervals of a graph. I hope it helps. Please reach out if you have any questions whatsoever.